Hi everyone. In this lesson I'm going to tell you about right angle trigonometry and introduce concepts such as the sine, cosine, and tangent ratios. Okay, so here's a right angle triangle, and you can see that I have marked the right angle here. This triangle is written in what's called standard position, so that the right angle is always in the bottom right corner of the triangle, and this angle here, which I'll mark in a moment, is our reference angle. So the reference angle we usually indicate by drawing an arc, and also by indicating that it's called theta. So that little circle there with a line through it is the Greek letter theta. A Greek person would say theta, and it's basically what we're going to use to represent an unknown angle. So you know that in mathematics class we often use x to represent an unknown variable, a variable number. In this case, we use theta to represent the angle that we don't know. And that's just a traditional convention. On the triangle, so now that we have our reference angle indicated, the rest of the triangle can be described using words, one of which you already know. So the long side of the triangle is known as the hypotenuse, and this side closest to the reference angle is called the adjacent side. Okay, adjacent is a fancy name for next to or near to, so that's why we call that the adjacent side. That's an N there. I don't know if you can tell. Okay, adjacent side. The remaining side, the one farthest from the angle, is called the opposite side. Okay? So really I'm just introducing this terminology. One of these words you already know, hypotenuse is always the longest side. And these other words, adjacent and opposite, I'm indicating them because we're going to make use of them later on in this lesson. Okay, so when we have a triangle, again, I'll just put in my reference angle, whoopsie. Put in my reference angle like so. And when we have, when we first start talking about right angle triangles, we often will make use of what's called the reference triangle. Reference triangle. And in this case, the reference triangle is a triangle which is drawn in standard position, so like this, with the right angle in the bottom right, and the angle of interest, our reference angle, in the bottom left. And then the three sides take on very interesting values. So the hypotenuse, the longest side, we always make that 1. We make that 1 for the hypotenuse. And then the other sides, they take on very interesting values, and you'll remember these perhaps from the trig trainer, but the adjacent side basically takes on the value of cosine of theta, and the opposite side takes on this value of sine of theta. Now you might be wondering now what it means to what cosine of theta is or what sine of theta is, and I'll say right now that cosine and sine and tan, which I haven't talked about yet, all refer to ratios. They all refer to ratios. And remember that ratios are just one thing divided by another. So really, they're fractions. The problem that a lot of people, the reason why a lot of people find trigonometry confusing is that although we in math class will represent these sometimes as ratios or as fractions, your calculator will change these to decimals, which isn't always very helpful. Okay, so one of the reasons why people find trigonometry confusing is they have to manage working with decimals and fractions and sometimes even ratios. And so there's a little bit of numerical fluency that is kind of assumed. Anyhow, so this is our reference triangle. I don't want to belabor the point, but this is our reference triangle. And again, I just want you to remember that the hypotenuse is always 1. The adjacent side is cosine of theta, and the opposite side is sine of theta. Okay, well, how do we make use of that? So here's a triangle. Again, I've used the same triangle each time, but what I want to point out is that let's say, for the sake of argument, that I chose my reference angle to be, I don't know what that looks like, but let's say 30 degrees. Okay? On my reference triangle, so again, this is the reference triangle. On the reference triangle, the hypotenuse is 1. On the adjacent side, I have cosine of 30 degrees, and on the opposite side, I have sine of 30 degrees. Now, these are numbers. Cosine of 30 degrees is a number. If you put that into your calculator, you'll get back a number, which is approximately 0.866. And likewise, if you put sine of 30 degrees into your calculator, you would get back an exact value, which is kind of fun, of 0.5. So this is what I mean about your calculator. If you put in cosine of 30 degrees, will give you this number, this decimal number. But really, the cosine the cosine is a ratio, and it's a ratio of the side length of the adjacent side length divided by the hypotenuse. And I'll make more mention of this in another one. So the cosine, let me just write this out here. So the cosine of an angle is really defined as the adjacent side divided by the hypotenuse. And likewise, the sine of an angle is defined as the opposite side length divided by the hypotenuse. So that's really what those things mean. And here I'm trying to make the connection between it written as a ratio and written as a decimal. Okay, I'm going to try and put this into a context with slightly more real numbers and a triangle that doesn't have a hypotenuse of 1. So here's an example, and you can see that I've chosen an angle of 37 degrees, and my hypotenuse is 5, and in this case we're meant to find this side length x. So to make concrete what I've been talking about with the reference triangle, I'm actually going to draw another triangle over here. I'm going to try and draw it slightly smaller. So in this case, here's 1. Here's 37 degrees. So 1 is the hypotenuse. My angle is 37 degrees because it has to be the same here as it is here. You'll see why in a second. And then this side is going to be cosine of 37 degrees, and this side is going to be sine of 37 degrees. I'm just going to pause for a second while I figure out what those are with my calculator. Okay, so I'm sorry for that. I had to go and work out what those ratios were in my calculator. So all I did was I worked out the cosine ratio, and here it is here. It's approximately 0.7986. And I worked out the sine of 37 degrees, and it's here, 0.6018. Okay, so now how am I going to use those numbers to actually answer my question? Well, here's the thing. You can see that on my hypotenuse, on my reference triangle, my hypotenuse is 1, right? We always make it 1. This triangle has a hypotenuse of 5. And although it might not be obvious, these triangles are similar triangles because they have an angle, that's the same, and another angle that's the same, so clearly the third angle has to be the same. So these two triangles have angle-angle similarity. Okay, well, if you look closely, you'll see that the scale factor is actually set up for me. If this is 1 and this is 5, my scale factor is 5 divided by 1, or just 5. Okay, so that means if I have my scale factor, I can work out the sides on my big triangle quite easily as long as I know what the sides are on my reference triangle. And so that's why I did those. So in this case, we're looking for the opposite side. And so in this case, I'm going to take this number, 0.6018, multiply it by 5, and get x. And if I do that, I get a number very, very close to 3. So in this case, x, x equals 0.61, nope, try again, 0.18 times 5, which is very, very close to 3. So x is 3. Okay? So that's how you can make use of a reference triangle to find a missing side length. In this case, that side length. Here's one more example. So in this case, I have another right angle triangle, and in this case I happen to know what the opposite side length is and the adjacent side length is, but I don't know what the angle is. So it'd be really great if I could figure out what my angle was, because, well, that's actually what I'm asked for. Since theta is since theta is unknown, it's implied that that's what I'm actually asked to find here. Now there are a few things that you could do here. For example, you could, and I'm actually going to solve this problem two ways. You don't know what the hypotenuse of this triangle is, but surely you could figure it out because you know the opposite side, you know the adjacent side, and so by applying the Pythagorean theorem, so I'll call this h for hypotenuse. So by applying the Pythagorean theorem, you know that h squared equals 5 squared plus 6 squared. So therefore h equals the square root of 25 plus 36 or just the square root of 61. So now my hypotenuse I have a square root of 61, and you can then use that to build your reference triangle. So for example, if you want to go to the reference triangle, you can do that. You know that this side has to be 1, and again, the scale factor here is always set up by your hypotenuse. This is why I actually figured out my hypotenuse. My hypotenuse is square root of 61, so that means that if I want to go from this triangle to this triangle, I have to divide all of my lengths by the square root of 61. So in other words, the adjacent side is 6 divided by the square root of 61, and the opposite side is 5 divided by the square root of 61. The angle I still don't know. So now I actually have a choice, because if you remember, this side by definition is the sine of theta, and this side is by definition the cosine of theta. So now here's what I mean. You can do this two ways. You could use either the sine ratio or you could use the cosine ratio, but they should both give you the same result so long as you do it properly. Let's do both one at a time. So I'll start with sine theta equals 5 divided by the square root of 61. Now here you can see that I have, on the left hand side, I have sine of theta. I actually just want to have theta by itself, so somehow I have to get rid of this sine. And this sine, although we haven't really, maybe don't know about these things yet, this sine is actually a function. It's operating on this angle theta. So I have to undo the sine operation. I have to undo the sine operation. And so what you would do here is just like if this were if this were like division, you would have to do the inverse operation. And it turns out there is actually an inverse operation for sine. It looks like this. Sine minus 1. So sine minus 1 of sine theta equals, again I have to do the same thing to both sides, sine minus 1 of 5 over square root 61. Zoom out a bit here. Oops. Okay, on the left-hand side, this works out really nicely because sine minus 1 undoes sine, so those two neutralize each other. So all that I'm left with on the left-hand side is theta. On the right-hand side, I have to take out my calculator and I have to do the operation in my calculator. Now this little guy, on most scientific calculators you get by doing the second, you do second sine. So you press the second button and then the sine button and then you put in your ratio. So I'm going to do that. Just hold on a second. Okay, I worked it out and I found that my angle is about 40 degrees. Okay, I'm going to do the exact same thing with the cosine ratio, and if all goes well, I should get the same number. So cosine theta equals 6 divided by square root of 61. I have to do my inverse cosine, inverse cosine of cosine theta equals inverse cosine of this ratio. And so now I have this one undoes that one, and I'm left with theta equals approximately, again I use my calculator, and wouldn't you know it, I get the exact same answer, 40 degrees. Okay, so with this example I hope that I've shown you how, if you're given side lengths and asked to find an angle, this is the procedure how you can do it. You can basically set up your sine ratio, for example here, but then you have to take the inverse side of both sides, and this, strictly speaking, has to be done with your calculator. We're not going to use other technologies like trig tables. Okay, and it doesn't really matter if you decide to use the sine ratio or the cosine ratio, you can get the same answer. Alright, I'm actually going to talk about one last thing before I end this lesson, and that was something I mentioned at the very beginning, and that was the tan ratio. So the tan ratio is actually the tan of an angle is actually the same as its slope. So you can see here in this picture, if this were the ground and here's my angle, this line has a slope to it. It has a certain slope. Okay, so we often talk about slopes in terms of lines, so if it helps you think about it, it's the slope of this line. And clearly the slope of that line has to do with this angle here. As this angle gets bigger, the slope of this line must also get bigger. And it turns out that the tangent ratio is actually what tells you about your slope. So now, forget about trigonometry for a second. If I asked you to figure out what the slope of this line was, I'm sure you could do that, because you would realize that that if I started here, my run was 6 and my rise was 5. My run was 6 and my rise was 5. So in this case, my slope would have to be, my rise is 5, so I have rise over run. So my slope is 5/6. So my tan of theta is 5/6. If I wanted to get the angle, well, guess what? I have to undo this tangent operation, this tangent function, so I'm going to go inverse tan of tan theta equals inverse tan of 5/6. Okay, again, these two undo each other, and all that I'm left with is theta equals, this side, the right side I do on my calculator, and lo and behold, I get the exact same thing as the others, 40 degrees. Okay, so there's nothing magical about trigonometry, or, well, if you want, everything is magical about trigonometry, because it all relates back to similar triangles, which are pretty magical. So this, if anything, is where the magic happens. The reference triangle that sets you up on the path to success. So that's why I always tell people, and you should do it too, draw a reference triangle whenever you're doing problems with trigonometry. They will help you immensely. Alright, that's all for today. Have a nice life, and don't forget to be awesome.